In this video, I will show you what happens when you bring a charged object near an insulator. So this is a sphere made from an insulating material that is neutral. Now, an insulator is an object where we do not have any electrons free to move around. Now, what do we have? We have atoms. So we have, let's say this is the positively charged nucleus, and I have some electrons moving around this nucleus. Now, I cannot really draw a lot of the electrons moving around. I will just show you. I will just include one minus sign near. Okay, and those are found pretty much in random positions around their nuclei. So here and here, they are everywhere. Okay, I'm gonna do some. Now, this is how I can describe an insulating material. The electrons that are present in the insulator need to be near their nuclei. They cannot move far away. They can move a little bit, but they cannot move far away like they can in conductors. So what happens when I bring a charged object like a charged rod near an insulating object, an insulating sphere in this case, and it is neutral? So every nucleus does have enough electrons around it to make it completely neutral. Now, because of the presence of these excess electrons here on the charged rod, we know that these electrons will repel any other electron around it. Now, this includes the electrons around our nuclei in the insulating sphere. Now, remember, these are constrained to be around their nuclei. They cannot be far away. They can move a little bit, but not much. Now, what that means practically, a little bit. So when I say that, so let me start another one. So when I say that they can move, doesn't work. All right, let's erase the whole thing and start again. So when I say that they can move, what I mean is that they will feel the repulsion from the excess negative charges on the charged rod, but because they need to be around their nuclei, they will just go to the side. They will all be to the right, from my perspective, to the right of their nuclei. Now, I'm drawing an object, a line to include those two. What I end up having here, every single atom of this insulating sphere will end up having their electrons shifted to the right. And this is because of the repulsion of the excess electrons on the charged rod. Now, what I have here, this is a huge number of microscopic dipoles. Why do I call them microscopic? Because they are at the atomic level. So every atom of this insulating sphere will become will have this kind of shape. So because I'm talking about every single atom of this sphere, I'm really talking about a huge number of these atoms having their electrons shifting to the right. So it is a large number of microscopic atomic level dipoles. They are dipoles because each atom now has two poles. It includes a charge separation. Their electron clouds have shifted to the right, and that left their nuclei a little bit off center, to the left. And all of these are going to be dipoles. I only have a few. I cannot show all of them, but you get the idea. Now I want to think. So I have a huge number of dipoles formed here, but what happens to the force? How are the two objects, the charged and the neutral, how are they interacting? Now, I will show you what happens on one of these dipoles, and the idea is the same for the rest. So let's take this one. I know that the excess electrons on the charged rod will repel this. Nope. Where is it? This one. Okay. Will repel this tiny dipole. Okay. And this will be the force from the rod, the charged rod, on the negative side of the dipole. I do know that the excess electrons of the charged rod will attract the positive side of the dipole, and because the positive side of the dipole is closer to the rod than what the negative side of the dipole is, there will be this attractive force will be stronger. Okay, this is the center of the dipole. And again, because the two forces are not balanced, the attractive force is greater. I do know that the net force on this tiny dipole, the net force will point to the left. So this charged rod attracts this dipole, and in exactly the same way, it attracts every single dipole on this insulating sphere. So that's why overall you see an attraction. This sphere should move, if it is light enough, will move towards the charged rod, and again you see an attraction. And you see an attraction between a charged object and a neutral object once again. Now the reason is that this charged rod has created all of these atomic level dipoles with their charges separating, and the two forces are not balanced. But attraction, once again, is not the way to detect if something is charged or not. Even if it is neutral, it will still be attracted. Now, these are, I do want to make a note, these are induced dipoles. And they are induced because they are created. They are induced by the presence of the charged rod. What happens if I take this away? Well, if you take this away, then there is no longer a repulsion on the electrons of the atoms, and those are going to be back to center. The nuclei and these electrons are going to have the same center. There will no longer be dipoles present in the insulating sphere. So this is going to go back to what it was at the beginning when the charged rod was far away. So these are induced dipoles. They are induced by the presence of the charged rod. And this we call this phenomenon the polarization of insulators. Okay, this phenomenon is called, the term we use is polarization. We polarize the insulator